Hi everybody, welcome back. So today we're going to be talking about curl and divergence. Now we need to get into this whole concept of curl and divergence. That way once we get into some of these bigger theorems like Green's theorem, Stokes' theorem, and divergence theorem, then we have the tools at our disposal to use them. Right. Now in here I'm going to say let F be a continuous vector field that's going to be defined in R space 3 with a P, Q, and R components respectively on the I, J, and K unit basis vectors. The curl is going to be defined as the curl for that vector field is given by the partial derivative of R with respect to Y minus the partial derivative of Q with respect to X. That's in the I component. The J component, it's the function P with respect to Z minus the first order derivative of R with respect to X. The K component is the function of Q with respect to X minus the derivative of the function P with respect to Y. So the big question is, how do we start using this? All right, so what we're going to do really quickly is we're actually going to start by moving backwards. We're actually going to go back into chapter 14. Now, in chapter 14, from chapter 14, we had what was known as your gradient. And the gradient was denoted like this. Well, in this particular case, what we're going to do is we're going to analyze this symbol. This symbol is known as del. Del is an operator. And it's an operator in the sense that addition, subtraction, division, those are all operators, right? They do something to this numerical value or to this function that we're looking at. The same thing with del. Del operates on a certain vector field, or it operates on a certain function a certain way. The way we define del, or the way we're going to be working with del, is that del is going to be just partial derivatives. That's all del really is at the end of the day. It's the operation that takes derivatives. And in this case, we're just going to match up the I, J, and K unit basis vectors with their appropriate derivatives. I component, that's the X component, so we're going to take a partial with respect to X. And then so on and so forth for the Y and the Z components. Now, more specifically, how do we get to this process here? How do we get to that definition? Well, again, as with everything, we actually have let's say, not a shortcut, but a good way to actually go ahead and think about this. If I want to identify the curl, in this particular case, or in this particular, let's say, process, what I'm going to do here is I'm going to say curl starts with the letter C. There's another operation that starts with the letter C. And that's this guy right here. What's that? That's a cross product. Oops, excuse me there. That's a cross product. What letter does cross product start with? C. So whenever we think of curl, we must think of a cross product, the cross product between the vector field and del, or del and the vector field. All right, now when we think of this cross product, we again do the I, J, and K unit basis vectors, and then we do del, which is just the partial derivatives operator, and then we do the vector field, P, Q, and R. Now, finding this determinant right here, or in this case, finding this cross product here, will actually lead you to this particular definition that we started with. Which, again, at the end of the day, just tells us, hey, we can use this definition, or we can just rely on these methods that we've developed so far. Which, me personally, I like using the methods that we've developed so far. This whole idea of taking a cross product and using this determinant to figure out what that cross product is. All right, so this is how we're working with this. Now, I'm going to list a couple theorems that are going to be very beneficial to us as we proceed to through the next few sections. All right, so I'm going to put pause on the video. I'm going to write down the theorems, and we'll come back and we'll talk about them in a little bit. All right, so here are the theorems that we're working with. Number one says that if we have this multivariable function and it has continuous second-order partial derivatives, then the curl of that vector field function must be 0. Okay. Next, or my apologies, sincerest apologies. This is a gradient vector field, must be 0. There we are. So now if if this vector field here is a conservative vector field, then the curl of that vector field must be 0. Number 3, if the vector field is defined on all of R space 3 whose components have first order partial derivatives and the curl of that vector field is 0, then we have a conservative vector field. All right. Now, again, this whole process of working with vector fields that are conservative is going to be very beneficial for us. However, as you can see here, we start calculating some of these curls for these conservative vector fields, and they turn out to be 0. All right, so we're going to have to be very careful with that as we move through. Sometimes it's a good thing, sometimes it's a bad thing. All right, so let's go ahead and let's look at an example. We want to determine if this given vector field, which is x squared y in the I component, plus xyz in the j component, minus x squared y squared in the k component, is a conservative vector field. All right, so what we then have to do in order to try to determine if it's a conservative vector field, right, we can go back to our previous methods in early chapter 16 and check some partial derivatives like we were doing back then. Instead, we can go through and we can check the curl here. Is the curl going to be equal to 0? That gives us an equivalence from when we started learning last time, or from what we started learning last time when we were trying to find those potential functions. Right? It deals with the exact same concept or that exact same process. All right. So all we have to do here is go through and figure out, is the curl of this vector field equal to 0? So this is one thing that we have to then observe. The curl of this vector field. We're going to have an I, a j, and a k component. My first is going to be partial with respect to x, then partial with respect to y, then partial with respect to z. And again, all of this is because the curl is defined as del cross the vector field. So del, that's the operator here, that's just a partial derivatives. And now I go through my vector field. My vector field in the x component, I have x squared y. In the y component, I have xyz. In the z component, I have negative x squared y squared. So all I have to do now is just take this determinant. So in the I component, I'm going to take the partial derivative of this function with respect to y. So taking the partial derivative with respect to y gets me negative 2 x squared y minus, I'm going to take this partial derivative here with respect to z, which should be just xy. All right, looking pretty good. Let's keep going. Minus the j component. J component, we're going to take this partial with respect to x. So that is now going to give me negative 2x y squared minus, and let's see what we're going to get here, minus, that's going to be 0, because this doesn't have a z component. All right, next, k component, so plus the k component. So partial of this function with respect to x, that's just yz, minus partial of the first function with respect to y, which should just leave us with x squared. Now again, all we have to do is check to see if this is 0. Now naturally this is not 0 because the first term, again, nothing cancels. Second term, one of the terms goes away, but we still have another term here. So naturally, because this is not 0, this vector field is not a conservative vector field. Is not a conservative vector field. All right, there we are. So that's how, again, we go through and we check this just really quickly. All right, we want to go through and we want to make sure we check it. If it is conservative, great. If it's not conservative, well, that's awesome. We're going to have some different methods to evaluate certain curves, certain surfaces, or certain items moving through a specific vector field. All right, so now let's go ahead and let's switch gears really quick over to divergence. So what I'm going to do here is, once again, let this vector field, let's say P, Q, and R, be a continuous vector field. All right, awesome. So the divergence is defined as the divergence of the vector field, which is just a partial of P with respect to x plus the partial of Q with respect to y plus the partial of R with respect to z. All right. So as we start looking at this divergence, we're now going to see, okay, well, given this divergence, it looks very, very similar to something, again, that we learned early on. All right. So what I want you to do is I want you to look at this, that we're defining the divergence of this vector field in terms of del and the vector field. Now I'm going to ask you, what does this first word start with? It starts with D for divergence. What is this operator? That is a dot product. That also starts with D. I'm a big fan of alliteration, specifically because alliteration helps with these so-called mnemonic devices, right? So if I start looking at a way to try to memorize, how do I find the curl? Well, curl cross product, right? There's my alliteration. How do I determine divergence? Well, divergence dot product. And all I have to do is remember that if I'm given a vector field, all I need to do is take the operator del with either the vector field I need to take the del with the vector field, and it's either taking a cross product or it's taking a dot product, one or the other. All right, so now that we have this, now that we can build upon this a little bit more, we know now curl and divergence. So let's see if we can do this example that I want to compute the divergence of f for this vector field, and we're going to call it x squared y in the I direction plus xyz in the j direction minus x squared y squared in the k direction. So if I want to take the divergence of f, again, all I have to do is a dot product between del, which is just a whole bunch of operators, partial derivative operators, and this is going to be with this vector field, x squared y, xyz, xyz, and finally negative x squared y squared. All right, so I'm going to multiply their individual respective components and then go ahead and add them. All right, so partial of this first function with respect to x, that should leave me with 2xy plus, take the partial derivative with respect to y for the second one, and that should just be xz. And finally, partial derivative with respect to z for that last term, which would be 0. So here's our divergence. Done. It's as straightforward as that. Got it. All right. Great. It's looking good so far. Now, let's take it up a notch, just a little bit more. All right, just to make sure that we kind of get what's happening here. So I want to verify that the divergence of the curl of f is equal to 0 for this vector field. Say that it's y z squared plus xy, oops, sorry, that's in the I component, xy in the j component, plus yz in the k component. All right, so let's go through. We're going to have to find the divergence of the curl of f. Now, what we're going to do is we're going to work from the inside out, because it looks like we have some function composition taking place here with these operators. So if we have function composition taking place with these operators, then we're going to go through and we're going to extract what we need. All right, so here we go. So the first thing I want to do is I want to identify what is the curl of f. So let's go ahead and let's find the curl of f. Now remember, curl starts with a C, therefore alliteration, curl cross product. We're going to be looking at del cross f. And we have the I component, the j component, and the k component. We have partials, 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 and then we have yz squared, we have xy, and we have yz. Let's go with the I component. The I component, partial of this function with respect to y, that's just going to be z, minus the partial with respect to z, that's going to be 0, minus the j component, that's going to be 0, minus 2yz, plus the k component, that's going to be y, minus z squared. There we are. All right, so now that we've calculated the curl, now we're going to go ahead and we're going to calculate the divergence. Oops, my apologies there. Now we're going to calculate the divergence of the curl of f. Now, the way that looks, that's going to be the divergence of what we just found here. So what I'm going to do is I'm going to put this in this specific component. This is going to be z in the I component. The next one's going to be plus 2yz in the j component, and the last one is plus y minus z squared in the k component. Perfect. So all I have to do now is just calculate that divergence. Now remember, divergence, D for divergence, then that means we got to go with dot product. So now I just need the dot product here. And the dot product is going to be with the partials, partial of x, partial of y, partial with respect to z, dot, and this is going to be with z, 2yz, and finally y minus z squared. And let's see. So first component here, partial with respect to x, that's going to be 0, plus partial with respect to y, that's going to be 2z. All right, plus the partial with respect to z, that's going to be minus 2z. All right, there it is. What can we see happen? Bam, we get 0. Awesome. Awesome. So it's looking really good right now for the items that we have. Right? We know how to work with curl, we know how to work with divergence. Now, again, we want to keep going with this whole process to see how we're going to be extracting this curl and this divergence. Here we go. Okay, so Now what it is that I want to do is I kind of want to look at Green's theorem real quick. All right. Now I'm going to give you a small version of Green's theorem. Oops. Excuse me here. So Green's theorem. We're going to be looking at the integral over a curve, and this is going to be for p dx plus q dy. Now, for Green's theorem, this is going to be equal to the double integral over some domain or over some region that the initial curve is enclosing, and this is going to be for the partial of q, with respect to x, minus the partial of p with respect to y, and this is going to be dA. Alright, now this will also, as we're going to come to find out, is going to be equal to this. Alright, just the line integral. Now, when we're working with Green's theorem, and I said that we wanted to work with Green's theorems specifically because what I want to do right now is I want to work with the curl of the vector field that's given here by Green's theorem. Alright, so this is going to operate under the assumption that we have some p and some q within our vector field that we're looking at. So when I try to look at my vector field here, I'm going to look at some p component, some p in the I component, and some q in the j component. And when this happens, again, Green's theorem is going to be satisfied here. So when I look at the curl for this vector field, this is the I, j, and k components, notice that I'm going to be taking the cross product so those are the operators, and then this is going to be of p, q, and 0. And again, 0 because we're only working with this R space 2 vector field. So this is going to give me in the I component, I'm going to have the partial of q, I'm just going to leave it as q with respect to z, minus, or actually there's no minus there, my apologies, simply because, excuse me. Alright, so here for the I component, it's going to be minus the partial of q with respect to z, and then we're going to have a minus j component. So the minus j component, again, that's going to be 0, and that's going to be minus the partial of p with respect to z. So it's going to be p with respect to z, and then we're going to get the plus the k coordinate here. This is going to be the partial of q with respect to x minus the partial of p with respect to y. All right. Now, looking at this here, this curl, we actually see that this k component is the very last component that we need for Green's theorem. So could we then only isolate this k component? So that's a big question. I want to isolate that k component. And there is going to be a way to isolate that k component if I take the curl and I dot this with the unit basis vector k. Now look at what that's going to do. It's going to take this curl, this negative partial of q with respect to z, plus the function of p with respect to z, and then we're going to have that q with respect to x and p with respect to y, and I'm going to dot this with the unit basis vector of 0, 0, 1. What that does is it just gives me this piece here. In other words, it gives me what I'm looking for, the partial derivative of q with respect to x minus the partial of p with respect to y. It gives me that individual component for the integrand in Green's theorem. Which means Green's theorem, if we observe Green's theorem, we can look at Green's theorem in this specific way. That when we're looking at a line integral as such over the curve, then we can use we can use the curl over this domain, curl of f, and that's going to be dot the k component. And this is going to be with respect to dA. All right. So again, using Green's theorem, we actually get this very beneficial aspect that we can use the curl, take that curl vector, and take the dot product with the unit basis vector for k, and that in itself is going to give us that integrand for this specific Green's theorem. All right. Now, anytime that we're talking about the curl, we're basically talking about a circulation around some curve C. All right. Now, what if we're not using Green's theorem? All right. What if we don't want to analyze this with respect to the curve? What if we want to analyze it with respect to the surface in which the curl is encompassing? All right. So for that, we actually get to use Green's theorem again, but this time we're going to use it for a divergence. All right. Using it with a divergence, or within normal form, we actually get to use a slight variation of Green's theorem. All right. Now, what is that slight variation going to be? Well, when we start looking at Green's theorem, what I'm going to be looking at is this particular case. The line integral over a curve, and what I'm going to use here is I'm going to use the exact properties that we were working with earlier. So I'm going to use this P. In this case, it's going to be P dy minus Q dx, like such. This is going to be equal to the double integral over some region that we are going to be encompassing, or some domain, again, that the curve is going to be enclosing. And this is going to give us the partial of P with respect to x plus the partial of q with respect to y. All right, so when we start looking at this, this is how we're going to be interpreting this theorem, all right, in using Green's theorem. Now, for this theorem, this is going to be the line integral of the vector field with respect to its normal vector. All right, so we got to keep that in mind. We're going to be using this in conjunction with its normal vector. All right, so if we got to keep it in line with its normal vector, again, the normal vector is going to give us something that we're going to need to see when we're talking about encompassing this curve. All right, now I'm going to give you an example to this, or more of a slight derivation to this. All right, so what I want at this point in time is I want some curve that I'm going to be observing. All right, so I'm going to be observing this curve, and I'm going to give this curve a certain orientation. We're going to be moving, or we're going to be traversing this curve in a counterclockwise direction, just like this. All right, now this region that is being enclosed here, this is going to be my region D. So this is going to be my region D. Now over here, this curve, this is just going to be curve C. All right, now we can generate any parametric curve that will be able to carve this specific curve out. It'll be able to traverse that curve. Now, more specifically, if we can find a position vector, then one of the items that we can talk about then is giving this a direction based off of that position vector. In other words, we can find this tangential vector, right? And this is going to be at any point in time, or any point out in space for this curve. We're going to be able to find this tangent vector. and it's going to be heading in the exact same direction. Now, the one aspect that I want for this is I want a normal vector. All right, I also want a normal vector, and I need to figure out what type of normal vector this is going to be. There we are. All right, so what I'm going to do really quickly then is I'm going to start defining that I'm going to have some r of t function, some r of t vector function, x in the I component, x of t in the I component, and y of t in the j component. All right, this should be able to capture whatever curve I have that I've outlined here. All right, now if I want the unit tangent vector, that way I can get the direction in which this is traversing, then naturally I'm just going to take the derivative and divide by its magnitude. Like such. All right. Now, this gets us our tangential component, our unit tangential component. Now what I want to focus on is I want to use this tangential component to get me this normal vector. Now, I want you to think back to how vectors operate, more specifically within lines. Think about orthogonality. If two lines are orthogonal to one another, what does that tell you? We know stuff about their cross products. Okay, great. That's awesome. We also know one more thing. Perpendicular lines, orthogonal lines, have slopes that are negative reciprocals of one another. What does that mean? Negative reciprocals, vector form. Well, let's think about that in vector form, negative reciprocals. If the first component is your x, your second component is your y, well, negative reciprocals just means that you interchange your x and your y, and you make one of them negative. So, if I wanted to entertain that idea and say that I wanted to build a normal vector based off of this unit tangent vector, well, all I need to do is switch the positions from my I component and my j component, and this is now going to be my y prime of t divided by the magnitude of the position vector, and that's going to be in the I coordinate, plus x prime of t r prime of t, and this is going to be in the j component. All right, and this is what we want to observe now. Because we are given this specific normal or this specific tangential, or sorry, we built this tangential vector based off of the position function, we can now extract this normal component. Awesome. All right, well, let's keep working with that. Right? So now what we want to do is we want to build upon this now that we have this normal vector. All right, so let's see how this is going to play out then. If we were using, if we were using Green's theorem, we would be looking at this here, p dy minus q dx, which is equal to the double integral, or actually, give me one second, PD, wow, my apologies, PDY, PDX, my apologies, plus QDY, there we go, is equal to the double integral over that domain or over that region of the partial of Q with respect to x minus the partial of p with respect to y, and this was all with respect to dA, right? But what we're doing here, what we're in the process of doing here, is we're looking to change all of those specific components. I forgot to make one of these negative. We're looking to switch all of those components that make up these tangential components, right? Or these normal components. In other words, given this vector field, what we then want to do is we then want to figure out what is normal to this specific vector field as we're traversing this curve. And if that's going to be the case, then all we need to do, if this was identified here, if this was identified as your p-value and this was identified as your q-value, then naturally what we then did is we switched them and then we made one of them positive. So what does that now look like for this specific integral? Well, that now looks like what we have here, right? This now looks like the circulation for this curve for p dy minus q dx, which is equal to the double integral over that domain, and this is now going to be for the partial of p with respect to x minus the partial of q with respect to y. And this is all dA. And these are the two forms of Green's theorem that we use. All right, so these two forms are the ones that we need for Green's theorem, right? And they're going to be slight variations of one another. Oh my goodness gracious, that was a plus right in here for that very last one. My apologies. Now, as I was getting to that last piece, what we want to do then is looking at this last piece, when we're trying to figure out how we're going to be working with this normal vector, typically the way we want normal vectors is normal vectors to a specific surface. Now, what that means for us is that this specific piece here can also be equal to the double integral over the region for the divergence of the vector field with respect to A. And that vector field is this initial vector field that we were given that we said we wanted to analyze. What is that vector P? And what is that component P and what is that component Q? And then we're able to find that divergence, which means we're going to be able to evaluate that specific integral. So knowing how to work with curl and divergence is very, very beneficial because, again, as we start getting into these line integrals a little bit more deeply, the basis of this is going to be enveloped right here when we're looking at curl and divergence. All right, so I hope you all enjoyed this. We're going to do some more Green's theorem once we actually get to that section. All right, so please stay tuned and stay safe.